Alright, what I wanted to talk about here, just briefly, is something called torque, which again you learned in year 12, and just a couple of little things I want to show you with this. Remember, torque is equal to a force times a distance, so we used it on pivoting beams and stuff like that. Remember the principle of equilibrium, rotational equilibrium, linear equilibrium, just reminding you of that. Now, the thing about the torque is that, as we said with force, to get an acceleration, you need a force. To get a torque, you need a, to get an angular acceleration, you need a torque. No torque, no angular acceleration. No force, no linear acceleration. Important to remember that. Now, when we initially used to do torques and stuff like that, what we used to do is we used to go, okay, we've got a beam or a pivot, and we'd say, okay, if this one's got a mass, then the clockwise torque, the torque this way, will be the force, which if that's the weight force, times that distance. So we'd say the torque, the clockwise, is equal to the mg times d. And we used to do that whole balancing thing. That's quite simple. But there's a couple of things. I want to first have a little talk about two-dimensional objects. What if, for example, I've got a car, something like that, and it's going around a corner, all right? And we want to work out a torque. Now, when a car is taking a right turn, it's going in that direction, it needs a centripetal force, right? So the car wants to push out this way, so it needs a force that way, frictional force, right? Let's imagine that actually that tire is lifted up and the frictional force is just coming from this one. If this is the pivot point, okay, if it's the center of mass and you've got a force, then what you've actually got is this force acting about this rotational point. It's trying to rotate this whole vehicle. So what I wanted to show you here with torques, this was sort of like one-dimensional torques. This is where we look at two-dimensional torques. And we know that our torque, when we did it, had to be at right angles to the point that went from where the torque was applied back to the center of rotation. So we would have taken a component and we would have taken this part of that force and multiplied it by this distance. And that would have been our torque. The whole vector doesn't get used. The part of the vector that goes in line with the center of rotation does not create a torque. So that would create a linear force. So we could do that. But what I want you to know is that when you want to do this, we can actually do it in a simpler way by drawing a line horizontal or parallel with the force and then taking a perpendicular distance. And if we take a perpendicular distance, then we can say the torque is equal to the full force times the perpendicular distance. So if you see that, that's what I've done. So it's going to come in useful when we do angular momentum in this unit, is this idea of a perpendicular distance. It's because we don't really concentrate on vectors in high school. This is all taken care of normally with vector notation. I will come back to that. So we've looked at torques, we've looked at them in a two-dimensional object, we've looked at them in a single object. We've said that you need a torque for an angular acceleration. I want to talk about torques on circular objects. Now, I've got a circle there, and I apply a force. This is really important, what I'm telling you now. And a lot of the stuff we do in physics, people don't understand the basics. Even physics teachers don't always understand some of the basic things really thoroughly. But if that's our force, and we apply it to the circular object, we could do that. We could maybe have a string going around the edge and we'd just pull on it. Then we'd have this force. Now the thing is, that force will produce a torque because it's not operating through the center of mass, right? So it will produce a torque, and the torque will be that force times this distance. So that distance there. So the torque will equal that force times that distance. Now the thing is this. It will also produce a linear acceleration. And the linear acceleration, so that force will also behave as if it's acting through the center, creating a linear acceleration. So torque is produced plus a linear acceleration. So normally what you do, if you did do this, and this object was say on ice or in space or something, not only would the object start to rotate this way, but the whole object would move in that direction. Don't forget that that happens. So if you actually want that object to stay where it is and you apply torque here, then you could put a nail or something through the center, and what would happen is that force that we said gets applied through the center would be resisted by the nail, and you'd get your perfect rotation. That is one of the ways you can stop that happening. There is another way. If you don't have a nail, right, and you have another force on the opposite side, we call this a force couple, then we get the same torque going in the clockwise direction. We get a linear force through the middle from this one, and we get a linear force that way from that one, and they cancel out. So it will spin without translating. So this whole idea of the linear force coming from the torque is very important.